Okay, I will begin. So here's the code. This is using the sample enclave code that comes with the SGX. To note when using this sample enclave is that even though the name is same, depending on what version of SGX you use, they're actually slightly different. The difference actually basically comes from uh, these areas you see here. You see at great syntax, you see here um, there are these functions they set as trusted and untrusted. And one notable difference here is some of these functions that they set as trusted are counted as deprecated in recent versions of SGX. And hence, when you try to compile an old version of an sample enclave in a recent version of SGX, they would notice that you're using deprecated code and would not allow you to compile. Okay, so that's the only thing you have to know if you want to make a attack code, because there's a lot of things you have to write, and it's kind of mind-boggling sometimes. So it's nice to actually use the many sample codes that the SGX gives. However, you should note that old versions and new versions have slight differences. So here we have the actual main function. So here is where the exploit starts. So we assume that we know the base address. So what that means is even though we don't have the okay, so I'll first show. So once you install the SGX SDK, you also have to set the environments. And and for recent versions of SGX, the default make from make is make hardware mode, but in 1.6 the default make is make simulation mode. So if you're using a rather recent version, you might have to check the make file to see if the default mode is sim or hardware, or else you have to set SGX mode hardware. Okay, so basically we assume that we uh, know the base address. So if you execute nap for simulation mode, it tells you right here what the base address is. However, if you want to test, if you have I should say if you're using hardware mode, if you're using hardware mode, mm, it's usually in here. And another extension paper on the guard's dilemma, which is SnakeGX, uses this maps and searches for ISGX. And ISGX is a old version of the driver. So legacy version of the driver uses ISGX, and recent version uses enclave something. So that's just the thing you have to know. So you could find it here, and actually SnakeGX, once executed, searches this proc file after finding its own PID, and then it opens it up and searches for the correct address to attack. So now, since we know the base address, simulation mode gives it to us, we just copy paste it, and as you see, the attack has succeeded, and um, we have a shell, which is not that special. Actually, having a shell is not too meaningful. However, we can check that the code is indeed injected and executed. So as for these positions, I tested this also in Microsoft Azure. I think Ubuntu 18 server. which has SGX hardware. It seems that there this also works. So these addresses they don't change. They only change if you go to the enclave.c enclave.c here, and if you add a function or change some things in here. I put this in during debugging, and this is because of this one line of function. It originally supposed to be 8317. However, because of that, this is AC27, and this also has to be ACEE, 8CEE, if it didn't have that secret function inside. Okay, so this you don't use it, but I used it for debugging. So we get the enclave base address, add the position to get the address of each of the functions within the enclave. And this was also for what should I say? This was also for debugging. So how do we get these addresses if you don't really know? So once you actually make the enclave, so originally file will look like this, but once you make it, you actually find enclave sign.so, and in here we actually have all the important functions that we need for sorry all the functions we need to conduct the exploit. And finally, for the write gadget, which is the key gadget that they used in the ROP exploit using CONT-Loop, you could find it. So actually the write gadget is, the paper also states that it's part of a function called doRdRend. I actually checked that this function exists in the most recent version of SGX SDK, and the definition is basically the same. So write gadget does function in the recent version of SGX SDK if you fire it up. However, the recent version seems to be a little different. We'll actually check that out later. So currently the most recent version we have is 2.18. It was updated a few weeks ago, I think. Which also okay. So this part 8CE5 from move EAX to RAX. So we move 32 bits from the RAX register into the RCX. The target, well, the target value of where the RCX is pointing to, and we move one to RAX, and we return. And once we return, okay, so once we return, where we return into is where the RIP, where the top of the stack is, which is the return address. So how we do this is, if you create a fake stack, and we'll pass this stack into using the continue execution, which will be fired first. The continue execution will place this stack, point RSP to this stack, so this will be the stack. Or what it always is just a stream of continue execution addresses. So once you return, no matter how many times the write gadget will go, it would always return to continue execution because the stack is only filled with this value. And I think the recent version of, I don't know when it was patched, I didn't check all versions, but the recent version moves the stack and potentially, actually interestingly, disrupted um, the attack I did. I didn't test too much on the recent version because time constraint, but still, that was very interesting. And here at point 50, we'll put the code in it will inject the code. Um, the paper was very vague as to where the code has to be injected. It just called it a proper place, so I just placed it in the stack. So this is the code we inject. As you remember, it was just a basic shell code, and here it is. So basically, once the continue execution starts, this context will be planted in. This context, what it does is it plants RAXs. If you remember, the RAX value, EAX would go into, so basically this 32-bit value would go into this address, and the RDI is the next context. So once the write gadget returns, it will use this RDI as a context for the next continue execution, and it will send the RIP as write gadget. So write gadget would fire up. It would overwrite this address with this value, and then it will return referring to this stack, and the stack is only filled with continue execution, and then so it will return to continue execution holding this variable context to be used, and following will continuously write onto the stack, and the final stage we send the RIP to the first point of the written address to execute the injected code, and we'll have a shell. That's the premise of the idea. This bottom commented out section is the shell code introduced in the paper. However, the problem is that this shell code wouldn't execute or wouldn't even parse. So I added this to show that it actually was injected. However, it doesn't recognize the ncru and crew instruction, because this instruction is specifically for the SGX um, hardware. So it's an enclave instruction. So if the CPU is not in SGX, it wouldn't recognize this instruction. And yes, so it's supposed to destroy the enclave, but we'll open the shell and then enclave will be destroyed and whatever. So to show how the attack works, um, where is it? I'll just so display how the attack will work. Okay, so we'll be breaking every write gadget execution, and I'll show you. Okay, so info registers. So as you see, all the registers are set as 0, and we see the RAX value is what we want, the RCX value, RDI value, and RSP value are all what we want. And so if we continue and point info reg again, we see it changed. So according to it, it's now the second one, and then now it's the third one. And like continuously, you see that the registers are being overwritten. So in a sense, this is a very basic ROP attack. However, what's more powerful, the SGX enables the attacker to control all registers. So basically, I wasn't able to do anything too special with this, but since you control the registers, you could actually conduct attacks and robo attacks, use rough gadgets that weren't possible. So just even the right gadget itself is not too special. It puts the RAX into the address the RCX points to, but since we control the registers, it becomes a catastrophe. So once we have put the final instruction in, if you see here, right around here, we see that as you see, we have the it seems to have picked the wrong number. However, the basic idea is that the instruction is planted in. So that's why once you execute it and give them the restart address, that's why we have the shell open. Okay, wait. So now here we go with the recent version of the SGX. first we need to source, and so for the for the SGX recent SGX, because if you see here the make file sets the hardware basically to hardware mode. Since SGX mode hardware, you have to explicitly state that the SGX mode is simulation. So this one does not work. So here they also give you, in simulation mode, they also give you the start of the address, and you see all this information. And but we have oh yeah, for debugging purposes, I added a what's breakpoint. Yeah, here you go. I added a breakpoint here for debugging. That's why that happens, but it wouldn't be different even if you don't debug, because it will just sh shoot out um, a segmentation fault. So okay, now let's go. So we'll show you where the problem is occurring. So the instruction is in general the same, however slightly different. So okay, so we see that we have reached the right gadget, which means that the continuous execution has successfully executed. Oh yeah, by the way, how I execute the continuous execution is a little problematic. However, I think I just did this for convenience. Is basically we just I shoot an assembly. I move the first variable into RDI and second variable in, and call the second variable, which is basically we put the context into the RDI and call the continue execution address, which is kind of very crude way of doing it, but nevertheless it works. So yes. Okay, so if we check the register, we see that all the registers set as 0. We have what we want in .ax. Continue info, right? And also again we see that the according things have been met. However, what we have to note is if you see the RSP, you see that it has incremented a lot. See, it has incremented quite a lot. As you see, it has incremented like from 190 to 5E0, because usually the stack itself doesn't increment. However, here you see that it actually incremented a lot by 0x80 if I'm correct, because the return address increments it by 0x80 in the continue execution, the changed continue execution. So if, what I mean is that if you see uh, if you sorry if you see the if you check the continue execution, oh, we need a little more. If you check the continue execution, we see that it has this value. So first I was confused when I saw this, and later when I checked the instruction, if return as this variable, it actually moves the stack, which is the cause of this problem. And this can be solved, but I just left it here because it causes an interesting bug. It's if, as you see, the top of the stack is now what we have written. We remember we write onto the stack. So what that causes is, so if you here, see here, so we have this here, and we see that we see what, okay, so you see that we moved the stack so far apart, we write it here. So the original, so basically we're moving the stack so fast, so quickly, that it actually causes the um, injection process to be kind of polluted in a sense. In a sense, it's getting polluted. So basically, yeah, so basically it doesn't work. So if you see the info frame, you see we're going to this address which would cause a segmentation fault. And this is why the attack doesn't work. Furthermore, furthermore, when you actually do execute this code without the so so if you do execute the code without this would shoot out a segmentation fault, but what also we should notice that it detects that we maliciously called the continue execution. So continue execution originally is supposed to be uh, re restore context after an exception has occurred. The signal handlers are saying like this is not an encrypted signal. Signal handler was triggered, which indicates that even if the stack is bypassed, this could cause a problem because basically enclave notices that this is a malicious call. Okay, thank you.